All right, I'll get started. Thank you all for coming. My name's Devin Odell. I'm an engineer at Fastly. I work on our core caching infrastructure, largely working on Varnish. I love performance work. I love debugging work. I'm a big concurrency nut. I used to live in Holland like 10 years ago. Haven't been in 10 years, so I'm actually really excited to be back here. If you, well, highly recommend just getting out and seeing stuff if you're not a resident. So just going to get started. So at Fastly, a lot of the time when people are giving talks, we're talking about sort of what it takes to build a globally distributed network, to send messages reliably on a large distributed cluster. But today, I want to sort of talk about a sort of more focused, lower level, in particular, a problem that we face on individual cache nodes. So we're a content delivery network. And so what we're doing is effectively caching customer content and delivering it to their users at a massive scale. And so obviously, like, that's a hard problem. But one of the problems is that on any particular cache node, we may need to share memory between processes. We may have multiple threads. And we need to be able to share information between these threads or processes safely. So if we've got a number of processes, these are able to sort of allocate and free memory within their own address space. And there's really no general purpose way for these processes to share memory between each other. And it might be useful for them to share information like indexes, cache eviction lists, whether that's LRU or something else. And sort of separate behaviors. Obviously, we could use multiple threads for this, but even if we're using like a general purpose allocator, we can't really control the lifetime of objects that are allocated within a private heap. So if we want the memory to live longer than the lifetime of the process, we still need to solve a similar problem. So we implemented a thing called microslab. It's a persistent, for some value of persistent, shared state memory allocator that processes can use to allocate alongside their heaps. And so what I want to talk about today is sort of not so much the allocator, but how we can give predictable performance guarantees of our allocator, and how we made it behave predictably under a high concurrent load. So first off, the kind of allocator we implemented is a slab allocator. And slab allocator hands out fixed size objects. And this is really nice from an implementation perspective because you can avoid problems with standard allocators or general purpose memory allocators like fragmentation, which is a really hard problem to solve and where a lot of overhead in memory allocation comes in. So what is a slab? A slab is just some contiguous region of memory. And the allocator is using this contiguous memory to return these fixed size objects from it. So if we want to allocate, we've got Lakitu here, and Lakitu is going to sort of represent a process. We're just going to call our allocation function, and it's going to return objects from sort of the head of this list. And if we free, we do sort of the same thing backwards. We're just going to produce the objects back to the list. So objects came from the front, they went back to the front. This is a stack. This sort of data structure is also known as a free list, frequently used for like object pooling and that kind of stuff. So we have lots of objects. Obviously, every piece of content we cache, we can treat as an object. So this, the metadata representation, this is actually a slab allocator is a really nice fit for that. So far, we just looked at a single process or single thread. So what happens if we add concurrency into the mix? And in particular, how can we think about the right way, or how can we reason about the right way to for the allocator to behave in the presence of simultaneous concurrent access to this list? Well, it can be useful first to define a protocol. Right? We think of protocols like HTTP or SMTP or something, but any interaction between bits of software we can think of as a protocol. In particular, we can define our allocator protocol as having sort of two interfaces, right? We have an allocation interface that returns us objects that we can use. We have a freeing interface that allows us to release objects. On top of this, we have some constraints. So if we allocate an object, it should never be valid for a subsequent allocation to return the same object unless it's been freed in the meantime. Similarly, you can't free the same object twice. So once we have this protocol in place, we can start to talk about how it will work in terms of an execution history. An execution history, pretty simply, it's just defining an ordering of requests and responses of our protocol. And so in this example here, we have two processes or threads, A and B. And in this case, A issued an allocation request, then B did, then A got a response, then B got a response. So hopefully it's not too hard to see that these 4 events can be permuted in 4 factorial ways. So that's 24 different ways. The more events that you have, obviously you get what's called state space explosion. But not all of them are valid. So the protocol we define puts constraints on what constitutes actually a valid execution history with respect to our allocator. So for instance, we can't have a thread receive an allocation response before it asks for it, because that breaks causality, and I happen to think that we have a pretty good model for physics. So it kind of bends my mind. So we say this has violated our protocol. So we'll put it back. And by putting these kind of constraints on our protocol, we can better reason about the correctness of our system. So it seems like there's another constraint that we need to put on how we even discuss our execution histories to be able to convince ourselves that our protocol is correct and will work correctly under contention. So one of the things that we can do is we can talk about sequential histories. So a sequential history is an execution history where request and response pairs within the protocol are indivisible, they're atomic. So any request is immediately followed by a response for that request. Anything in the middle makes it not a sequential history anymore, it's not valid. So this provides us an atomicity guarantee. And atomicity seems like a nice property to have in a concurrent system. So what does a sequential history look like? Well, so here's an example. So every request is immediately followed by a response, which is maybe easier if it's they're grouped a little bit. Our previous history was not a sequential history because the requests and responses were interleaved with each other. And so what this means is for a sequentially consistent allocator, no thread should be able to begin an allocation before a previous thread's allocation or free operation has completed. And also notice that while we can't interleave requests and responses, we can still interleave request and response pairs and yield a valid sequential history. And the notion of what we're allowed to reorder and consider valid is actually really important. So just keep in mind that reorderings are still valid even in a sequential history. So let's look at kind of what we have right now from a code perspective. If we were just going to implement a free list as a stack, this might be what we have, right? We read from the head, we read the next pointer and set it to the head, and then we return the head of the stack. And that's just going to pop an element. Freeing just puts it back onto the head of the list. So what do we need to add here to guarantee some kind of sequential consistency? Well, we can just use locks, right? Locks are basically the canonical solution in software to sharing memory in multiprocessor systems. They're easy to reason about. This is arguable, but they're easy to reason about individually because they serialize, and the serialization creates a sequential behavior. But to really understand why this happens, we really need to look at what a lock is and how it works. There's many different implementations of locks, general purpose locks. For simplicity's sake, I'm going to be talking about a particular kind of spinlock, which is a test and set lock. So spinlock is a mutex, a lock that attempts to acquire its lock resource. While it can't, it spins, constantly trying to acquire. So with the test and set lock, we're using a test and set instruction provided by the hardware. And what this does is that it effectively gets a snapshot of the current value of memory. It sets the value and then tells you what the value was that was read. So if the value was already locked, the resource is already locked, and we spin. And this sort of follow this right-hand side of the flowchart. If the snapshot was unlocked, the test and set operation has atomically set it to locked, and we have acquired the lock. Unlocking is really simple. All we have to do is atomically set the value to unlocked. Because part of, haven't sort of defined a locking protocol, but right, you can't have somebody who's not the lock owner unlock the lock. So this is why unlocking is simple. So this is what an implementation of spinlock might look like in the C language. So if we assume that we have an interface for our atomic test and set operation, Concurrency Kit, actually this lock is sort of a simplified derived version from one of Concurrency Kit's spinlocks. Provides these atomic primitives that we can use to sort of build up our concurrent data structures and build things like locking primitives. So this looks right based on what I've said, but can we define the correctness of the lock formally? Well, because an atomic operation is sort of by definition indivisible, any atomic operations to the sort of M variable, our mutex, are sequentially consistent amongst themselves. So there's a couple of things to notice here. First is that this test and set operation is really embedded in this larger operation of calling the locking function and returning from the locking function. And second, in the case of multiple threads, so let's imagine that we have another thread B that previously held the lock, and it's unlocking it before A acquires the lock. So this is actually a stronger constraint than sequential consistency actually provides, because sequential consistency would allow us to reorder these operations, because we're allowed to reorder pairs. That would yield an invalid history for the lock, because A is not allowed to acquire a held lock, right? So we're not allowed to reorder these. So if we've concluded that out of the set of execution histories, there's a subset of those that satisfy this sequential consistency property, it seems like we're moving towards an even stricter subset of those that satisfies an even stricter property. And it happens that the term that we're looking for is linearizable, or linearizability. So a linearizable history is a sequential history that additionally states that responses to requests may not be reordered with respect to each other. So if you have a response from a request, there is a guaranteed global total observed order, and no other responses could appear in the system to have occurred before that response. Linearizability, by the way, was defined by the Herlihy-Wing paper that I showed, also defining sequential histories a few slides back. So what about linearizability is actually better? So the Atiyah-Welch paper actually gives a number of properties, but points out two. Number one, we have sort of a guarantee of global ordering. We have a guarantee of global ordering of operations. And sequential histories are only defined at an individual process level. So when we have concurrency, we have to have something stronger than this, which is that global ordering. So two of these beneficial properties of linearizable histories over sequential histories are that it's an easier property to use for formal verification of software, because by definition, we're preserving a global ordering of operations. And secondly, linearizing provides compositional properties on objects. And this is really great because locks aren't compositional. We'll see why later. But if you can prove linearization on an object, all operations that linearize on that object linearize as well. So any operation is, any history is a linearized history, which is a correct history. In contrast, a sequential history requires you to think about all orderings on all objects and all processes together. And this is really hard to do. You still get your state space explosion. So given this definition, we might think that this is like the only valid execution history that's linearizable. But notice that if A enters the lock function between B's store, response, and unlocked, we still haven't broken the correctness of the protocol. And in fact, we can even reorder this more and maintain a correct behavior. So it seems like there's something about these instantaneous moments in a linearized history that we can think about. Linearizability prevents us from being able to reorder these request and response pairs. So we have these moments, these linearization points that are actually where this atomic operation that may be composed of multiple steps appears to complete. And something's very clearly special about these two atomic operations in terms of a linearizable history. So this is an excerpt from Leslie Lamport's paper that's credited with coining the term linearizable. And what he's talking about is enqueuing and dequeuing elements on a concurrent queue. And what he found in this paper that actually predates me by a few months he's telling us that it's sufficient for there to be this single atomic moment in our functions, instead of insisting that the entire function itself is atomic. This is the linearization point. In functions that use the lock-based synchronization plan, the moments are basically any time within the lock's critical section. So any time in between the lock and unlock operation, you can consider to be a linearized moment. And in the case of the lock itself, the lock linearizes. We linearize on our atomic test and set, and we linearize on our atomic store. So we know now, and we have formal basis to verify the correctness of our locking mechanism, but we haven't looked at performance. One of our criteria is that we really need to perform well, at least degrade gracefully under a highly concurrent load. Performance is kind of really a nebulous term, and so what I'm actually talking about here is predictability. Can we predict the performance of our system as we add concurrent load to it? Well, let's take a look at the throughput of our lock. So this graph is representing the number of lock, allocate, unlock, or lock free unlock, lock, allocate, free, unlock operations, the throughput of those that you can do. And this is per second, but was taken over a 10-second period on a 2-socket Xeon with 16 physical cores. So with no contention, we see that it's taking about like 18 nanoseconds to do an allocation in free. That's really great, but this is terrible, right? We add one contending thread, and all of a sudden, our performance has dropped by an order of magnitude, a huge factor. And the performance continues to degrade as we add more threads, which is actually maybe easier if we look at a logarithmic plot of this graph. So we're crossing nearly 4 orders of magnitude in throughput degradation as we add contending processes on the spinlock. And once we get to 16, we're effectively only able to do about 100,000 allocations and frees in a second. So this is really bounding the performance of our allocator, right? We can't do more than this, and this is because of the lock. Well, let's think maybe we can do something with the lock to improve it, right? Recall that the test and set operation reads a value, sets a value, and returns the value that was read. But it's setting a value every time, and this seems wasteful because if we're not acquiring the lock, then why are we writing to memory? Like, that seems ridiculous. So we can do something like this. If we fail to do the test and set, we can just try a cheaper non-atomic read. This would avoid writing every time through the loop, and we avoid system issues like hash invalidation, bus contention. I'm not really going to get deep into that, but those would be reasons that the previous incarnation of spinlock would be slow. But at first blush, it really appears that this lock is incorrect, right? So what happens when we have multiple processes reading that the locked state is no longer unlocked? Aren't they going to race? Well, technically, yes. So a race condition is just a system behavior where the output of the system is dependent on the sequence or timing of other uncontrollable events. It does not define buggy behavior, although it can be. But therefore, because it's not per se a bug, it can be safe to race. They're only bugs when the events occur out of the order that was intended by the programmer, out of the order defined perhaps by your protocol if you formalized it. Because linearization provides us a total order, and we have the atomic test and set acting as a linearization point, we're guaranteed that even though we race on the state of the m variable, we will never have multiple lock owners. So does this actually help throughput? Well, a little bit. It's getting there, but importantly, we're not getting good predictable throughput. So maybe we can do something else. Maybe we can implement a back-off algorithm, and maybe we think that this might be bad because maybe we just spin on our own state. This is local state. This is not shared state. Maybe we think that that will help reduce memory pressure because the compiler can optimize this into register access and spin on reading a register instead of trying to read from a cache line that's getting invalidated every time the lock is acquired. But maybe we sleep too long, right? The back-off, we're not reading the state, so there's nothing saying that when we wake up, we didn't sleep for longer than we could have. well, does this actually happen? Like, is that the case? Well, no. Actually, this works a lot better. It turns out that the local state, largely due to cache invalidation, helps significantly in throughput. But this kink in the graph right around x equals 2 is still really, really depressing. So we could probably try more tricks. But it seems like anytime we do something to improve the lock performance, we're really only changing a coefficient in this exponential decay. So in order to understand why this is actually a property intrinsic to locks, we need to make a quick diversion into something called a progress guarantee. So let's say that we've got 2 threads and some spin lock that's visible to both threads. The first thread enters the function, it swaps the state to lock, and it exits. And meanwhile, the other thread comes in and it wants to grab the lock, but of course it can't. So it's halted in the spin lock, and how long it has to wait is entirely dependent on how long the top thread holds the lock for. We can say that there's contention on this lock even though nobody else is trying to acquire it in the system. And this behavior, this lack of progress by other people who want to make progress, other threads who want to make progress, is why we get bounded. So we can look towards perhaps lock freedom. Maybe that'll help. What is lock freedom? A function is lock free if at all times, if at any point in an execution history, at least one thread is guaranteed to be making progress. There's other classes of non-blocking algorithms, but we'll look at lock freedom. It seems like this can help us avoid this sort of queuing effect that we're seeing by waiters on our lock resource. So maybe let's just go back to our original implementation and let's see if we can make a lock-free implementation. We need to use a non-blocking algorithm. We'll take a look at that. So how do we actually get into the world of non-blocking algorithms? Well, in particular, we're not limited to this atomic test and set operation. So processors provide a plethora of atomic primitives that we can use. One of these is a compare and swap operation. And for our purposes, this is what we'll use. So it's called compare and swap because we compare a value with some pointer, some memory stored in a pointer for equality. If they're not equal, then we just return false. If they are equal, then we overwrite the contents of that memory with some other value. So we swap a new value in and return true. And of course, all of this is done atomically. So like basically a little tiny critical section on the processor. So let's see how we can apply this to our allocator. Well, this is how our function might look in C. First, we're going to read the state of our stack, just like we did in the non-concurrent and the locked implementation. We read the head of the stack. We read the stack, the next element from the stack head. And here we have variables A and B corresponding with A and B at the diagram at the top. Next, we're going to try to update the head of the stack using our compare and swap. We're trying to modify A to B. So if we succeeded, then A was popped off of the list, and B, its successor, is now the head of the list. But what if the compare and swap returns false? Well, how can that happen? So maybe let's add some colors. If the compare and swap returns false, then perhaps the head pointer was changed to something else in the meantime. Well, why would that happen? So maybe a free happened, and now A is the second element in the list, right? Some other concurrent process came in called a free. Head pointer is no longer valid. So our compare and swap will fail because the state's changed. Or maybe another allocation happened and A got popped off of the list by some other concurrent process, and now B is at the head of the list. Well, this seems like what we were trying to do. This is, in fact, what we were trying to do in our original thread. And this sounds like another race condition. It is. But the compare and swap serves as a linearization point because it's able to detect that the state of our structure has changed from under us. And because we know that our state is different, we can retry our operation. But super importantly, we know that if we failed because somebody else succeeded. So this gives us lock freedom. We know that at any point, if we fail to do something, it is because some other operation on the structure succeeded. And this gives us a throughput guarantee that we did not have before with our lock-based implementation. So just quickly, let's look at freeing. It follows a similar strategy in that we're going to try to produce something to the head of the stack as opposed to consume, but we're going to swap something into the head of the stack. We're just going to swap it in. It's pretty straightforward. So this looks good. So what happens if we have a bunch of threads contending on this or trying to run this at the same time? Let's take a look at an example sort of history. So imagine that this laketu is a first thread. It wants to allocate an object. It's going to execute everything up until the compare and swap. So it's read the head pointer. It's read the next pointer. Everything's great. But then real life happens, and it gets preempted, and something else is running. So another thread's going to come in, and it's going to pop a value off the stack. And because the first thread hasn't hit its linearization point, this is entirely fine. So it completes, and it gets A. Right? Let's play this game again. We have another thread that comes in, and it's going to do the same thing. OK, well, now that thread has B. Well, in the meantime, let's say this second thread that popped A off the stack decides that it's done with A, and it's going to push it back onto the stack. Maybe you can see a problem already. As soon as we go back to this function, or this thread, who's already observed A as being the head of the stack, as far as it can tell, the state is still the same. But it thought that B was the next element. So when it does its compare and swap operation, we've set the head of the stack to B. So this is a bug, clearly. And furthermore, we don't even actually know what the state of B is. It's probably not even pointing at C anymore because somebody else was using it. Especially if you're talking about an allocator where the stack state is probably in line with the allocation as it is in uselab. So as soon as you get an allocation, you can change the contents, and all of a sudden your linkage is entirely broken. This is called the ABA problem. And note that this is really only a problem for us because we've specified that we have a workload with multiple contending producers and consumers. There are cases with single producer, single consumer workloads where the ABA problem simply can't pop up. And it's worth considering what your workload is before you go about trying to solve the ABA problem, because it takes at least time overhead and potentially also memory overhead, and our solution will take both memory and time overhead. It is something that we have to solve. So a common approach for this is to encode some additional state into our stack head. In particular, we can have a generation counter. And this keeps track of the number of times an allocation has happened. So it's basically like a generation of the stack. It continues to evolve with the lifetime or the state of the list. And in particular, if we pop B and then push B and then push A, the generation counter is going to have changed. So we can't run into the ABA problem with this. So how do we actually implement this? Well, instead of having these local object pointers, we're actually going to try to swap entire slab structures in. We'll see why in a minute, but we're going to be using this primitive called decas, which is a double cas, which is basically a compare and swap, but it's on a double wide value. And so this also means that this generation counter and the pointer have to be contiguous in memory. And it's actually worth noting that there's a reason here that we're reading the generation counter before the head. So it's not true for this allocator, but for a general purpose stack, it's entirely valid for perhaps the same item to be on a stack twice, right? Like I can come up with cases where we've got stats items that need to be processed. Maybe they need to be processed twice, right? So if we don't read our generation counter first, then it's possible that A gets inserted into the stack twice, and some other process read the generation counter and then reads A as the stack head, but it's got an old snapshot of the generation. If you read the generation counter first, that can't happen. Or I'm sorry, reads the head and then reads the generation counter. Freeing stays the same, actually. The free operation only changes the head pointer. It doesn't rely on additional state of the stack like our allocation does. Our allocation relies on the next pointer as well, which is why we get the ABA problem. So ABA is really only affecting us if we're relying on state in multiple pieces of our structure. OK, so now we've defined a correct concurrent protocol for our free list as an allocator. We've got this double cas generation counter allocate. We've got this free operation that puts these objects back onto our free list. Let's see what their throughput looks like. It's pretty great, right? predictable. We add contention, we see the same performance. We see the same throughput. Notice that our throughput is actually lower in the absence of contention. And this is easy to explain because in the absence of contention, we actually have a lot more work to do, right? We have this loop. We have a compare and swap operation. Atomic primitives are not cheap, right? They can provide us means to get predictability, but they are at the cost of upfront latency. If we look at the logarithmic graph, it's also looking pretty great. So it looks like we basically have linear performance here, regardless of contention. So why is this? Well, to answer this, we actually need to look at the latency, not the throughput, because latency is actually what's defining our predictability, right? We say that something's predictable if we can say this operation will complete in some bounded time, right? And throughput doesn't tell you that. Throughput tells you how many things you do, but it doesn't tell you how long it takes to do any of them. So we can have all of this jitter. This is our test and set lock, the naive version. And we see this is a plot of quartiles, by the way. The y-axis is number of CPU cycles. X-axis is number of threads. The numbers are plotted with the top 1% of latencies taken off the top to try to avoid accounting for or to try to account for jitter in the system. And this is based off of 1 million samples. So we see that there's a ton of jitter between, or deviation effectively, between our 75th percentile and 100th percentile. And especially from 0 to 100 percentile, there's just a ton of jitter, up to 300,000 cycles per operation. I haven't talked much about pthreads, but I suspect some of you are using pthreads and would like to know how it works. In particular, pthreads are good to consider in cases where you have more threads than you have available cores, which is really not where you want to use spin locks. So we see that pthread latencies are, the average case is sort of all over the place too. In our previous graph, average case is really very low. But in pthreads, it's sort of all over the place, and this kind of has to do, this was on Linux, it has to do with the implementation. I can talk about that later. But our y-scale is still in the same order of magnitude. Well, with our exponential backoff version, we can see that we've dropped cycle count by an order of magnitude. And it's really this reduction in latency that gave us the better throughput. But the reason that it degraded is still because we have this huge variation in time. We don't have progress guarantees, and this lack of progress guarantee is making our system unpredictable. If we look at our concurrent data structure, this is exactly what we want to see. Everything is very well bounded. There's not much deviation. We're in 2 orders of magnitude down from our exponential backoff, and we have very little jitter. The spike here is because the system has 16 cores, and as much as I try, I can't make every process stop running. Good. So takeaways. Safely racing processes and threads with each other is not only common, but it's kind of required if we want to get predictable behavior from our algorithms and data structures, from our systems. It's a crucial part of the process. So we saw how racing waiters on a spin lock could improve the throughput there. We saw how taking sharing state away can improve the throughput further, which isn't racing, but it's good to know. And we also saw how our concurrent allocator races processes against each other, and how linearization is a property that allows us to do this safely. If you're interested in more about this allocator, in particular, I haven't talked about how we get memory, how we optimize for having multiple threads, various other things. There's a lot of code that's not talked about, although including how 3 different ways of getting the memory. I think it's like 500 lines of C with a fair bit of comments. So definitely check it out. Right now, this is forwarding to the GitHub page, but planning project page, but I'm planning on putting something else up as well. Before I sign off, I want to thank my colleague Nathan Taylor, who helped out a lot with the slides, giving them a consistent total order. He also gave this talk at Surge, so maybe you saw this if you were there. If not, thank you for coming to my talk, and happy to take questions now. Yes?
Threads are basically trying to race. Are you basically pegging all the cores to CPU utilization?
The question is, if all threads are racing, are you pegging all of the cores? Are you talking about the spinlock case? Sure. So the spinlock case, definitely, right? There is a theoretical pathological case where that could be possible with our retry-based lock-free algorithm. There's a really great paper. Where is it? These two, by Luchenga, Moore, and Shavit, and Finch, and then also Alistair and Hillel and Shavit, which are obstruction-free algorithms can be practically weight-free, and lock-free algorithms, are they weight-free? Weight freedom is a property that I didn't really describe, but it says that out of a number of in threads, all threads make progress within a bounded time, which is a stricter property than lock freedom. And what these papers find is that actually if you implement a stochastic scheduler, lock-free algorithms do have a bound for how long it will take. And effectively, you can think of that because you actually have a bounded number of threads as well. And with random scheduling, sure. So yes, it's possible. I've never actually seen that be a case. Was there another question over here?
Just a small question about a bit of code on one of your slides.
Okay.
The lock-free version that
This one?
yeah, you mentioned something about it being important that the generation is read before the head.
Yes.
In this case, would it be possible that the compiler reorders those?
Thank you. So this is something that I've left out entirely just to keep it simple. So the question is it possible that the compiler reorders these? Yes, it is. So maybe not if these are declared as volatile. Both of them have to be declared as volatile. The compiler will only not reorder volatile pointers or volatile members with respect to other volatile members. It can still reorder them with others. But on top of that, there's also a bit of stuff about hardware, and in particular, memory ordering. So even if the compiler doesn't reorder them, it's possible that your system under the hood will reorder these memory accesses. So you need to use what's called a memory barrier. I haven't talked about that here. It is in the code. If you look at uslab.io at the GitHub page, so you can see where you would insert the barriers. But effectively, you need to have a barrier to ensure that between your read of the generation and the head, those operations weren't executed out of order by another processor. Intel processors, is anybody not using Intel processors, like maybe Power or Spark or, yeah, okay, so you probably don't care. ARM? Any ARM? Okay, so ARM has relaxed memory ordering, which is effectively what you had with Alpha. Maybe you've heard all of the people joking about Alpha and how you can't rely on anything. Alpha reorders all memory accesses. Stores can be reordered by the processor in a multi-socket system with respect to other stores and loads. So this property, you need to use, if you want a purely correct version, you have to understand your system. You have to understand, use memory barriers. Getting to that, more recommended readings. I will tweet out links to these slides. They are already up. I gave the talk at Strangeloop in September. What Every Programmer Should Know About Memory by Ulrich Drepper. And this very well explains memory considerations and memory models and compiler considerations that you need to consider when doing any programming, not just lock-free programming. Yes? In this implementation, decas is required. So that's a good point because it's not always available. Other processors don't even implement compare and swap. They implement something called load link store conditional. You can implement compare and swap in terms of LLSC and LLSC in terms of compare and swap. So they're similar interfaces, but there are other problems with that. So not going to get into that too much, but if the system doesn't require decas, you can do another thing, which is if it was really nasty, if your system doesn't use all bits of your pointer, you can encode a generation into the top or bottom bits of the pointer that aren't used. Practically, that can be a problem if you don't have that many bits and you have overflow, but then you only get ABA if you overflow exactly to the same spot at the same time, which decreases with more bits, which technically you have, but you're never going to have like 64 bits of wraparound ever as long as we're alive. So yeah. You can also avoid it by choosing to use a different model, right? If we use lock-free algorithms for logging, for instance, so we queue log stuff so that we're not doing any like even memory I/O except for a single pointer to do writes out for logs. So we batch a bunch of log requests, put them in a stack, and then pop them. So we have multiple producers, but single consumer. And in that case, we don't need to care about ABA. Or, yeah. Well, thank you. I'm happy to answer more questions after.